Hello again. I thought we would do some fundamental problems from Chapter 2 on strain. Okay, so Chapter 2, as you recall, strain, fairly short chapter, right? We talked about a couple of key elements in the chapter, and let's just review those real quick since it's such a short chapter. We'll talk about a couple of these items. The first thing is we remembered that strain itself, epsilon, is just equal to delta over L, or L naught. That is to say, the change in length over the original length. That's all strain is. And we said that it's non-dimensional. So sometimes you'll see in inches per inch or millimeters per millimeter. And of course those are the same value because they don't have any dimension really. And that's for axial strain. So that's if we pull on a bar like that with a load P, where this is L naught, right, or L, and it gets some longer length L prime, and of course this being the difference between those two. Then we said for shear strain, a little more confusing, where we start off with a rectangle, right, and we shear that rectangle and it becomes parallelogram. I know a rectangle is a special parallelogram, but nevertheless, this angle here, gamma, is the shear strain. And the other way to look at that is if this angle is theta, right, we would say that gamma, the shear strain, is equal to pi over 2 minus theta. It's just straightforward. And of course, shear goes like that, right? So one of the things I noticed is, just to remind you, to have a shearing force, right, you have a force this way and it's balanced by a force that way. For axial, right, we have a force this way balanced by a force that way. So this is axial and this is shear. Now if something's in pure shear, it has to be if I have a panel and I shear this, I have to react that down here. Well, that creates a moment. So I have to balance that moment this way and that way. And that's where you get a red pen out here. That's when you get the shearing action that does this, right? That's how you get that shearing action. Okay. So again, this one is shear strain here. And this is, of course, axial strain. And that's pretty much all there is to it. Pretty much all there is to it. Everything after that is geometry and trigonometry. So let's look at some of these fundamental problems that are in the book. And again, just as a reminder, the fundamental problems, of course, you have them in your e-text as well, but they're given here. We're going to work a few of these, not all of them. But then the answers are in the back of the book, back here. Here's all the answers, and they're worked for you. So we're going to work a couple of these, just help guide you through them. And again, I'll let you do some on your own. The key to these things and the key to your success is don't look at this first. Try to solve these. And then if you can't do it, see how they did it in the back. Or to confirm what you did is correct. The other thing is, again, when you're working problems, homework problems in particular, work them first yourself. And then you'll note that there are answers, again, back here in the back, answers to selected problems in the back of your text. It's in your e-text as well. It may be in the appendices, but it's in there. And you'll note that if it has an asterisk by it, like this one, the answer is not there. So every fourth problem does not have an answer in the back of the book. Gosh, where do you think I'm going to get quiz problems and test problems from? So let's look at some of these fundamental problems. Okay. Pretty straightforward. Again, we're going to involve a lot of trig and a lot of geometry and occasionally a little calculus. So let's look at the first one. We're going to look at F2-1. All right. And since they do a much better job on the graphics than I do, let's take a look at. Oh, I didn't want to go that much. There we go. So here's the problem. When force P is applied to the rigid arm. Now note, when they say rigid arm, that means it does not deflect. Right, we have a rigid arm, ABC. Point B displaces vertically downward through a distance of 0.2 millimeters. Determine the normal strain in the wires CD. We don't even need forces. We don't need forces. We can go straight to strain to strain. And this one's real easy, right? You have a rigid bar, starts off here. Oops, let me get in the picture. There we go. A rigid bar, and we know that it's going to deflect downward. And we're given this distance from B. This is 400 millimeters. And then from here to here is another 200 millimeters. Okay, and we know that this distance is 0.2 millimeters, so it deflects down 0.2. We can just do a ratio, right? We can say that 0.2 is to 400 what x is to 600, right? Because this total is 600. And that's going to tell us that x is 0.3. Right, so x is 0.3 millimeters. Now note that we kept all the units the same. Right, so we have millimeters over millimeters strain, millimeters over millimeters. So this distance is 0.3 millimeters. Well, now we know the deflection. To get the strain, right, strain is just equal to delta over L naught. And we know that, therefore, strain is going to be equal to delta, which is 0.3, over the original length, which is 300. Those are all in millimeters, right? And so the strain is just equal to 0.001. And if you wish, you can say millimeters per millimeter. Now, if the book asks you to use proper units, then use proper units. But that's all there is to it. All right? So we had our original rigid bar. We deflected it down. We just took the ratios of those distances to get the new distance. And then we said that strain is just delta over L naught. There's our strain. Okay, so that was easy, right? Sure. Let's look at F2-2. A little more complicated, not much. Again, I'm going to use the picture in the book right here. So we have another rigid arm pinned at A and supported at B and C with cables. Now, in this case, we're going to rotate clockwise about pin A through an angle of 0.02 degrees. And they want us to determine the normal strain in the wires BD and CE. And there's a load here. We don't care about the load in this case. All we're interested in is in that strain. So once again, we have this bar, and we're going to rotate it. But now instead of rotating it and giving us a distance, a delta, they're giving us an angular rotation, 0.02 degrees. Well, of course, we can't live with degrees, can we? We have to convert that to radians. So let's just draw a picture here. Make sure I stay in the camera. So here's our bar. And we're just going to rotate down, pinned about that point. And that's 0.02 degrees. And this point is at 600 millimeters. And it's 400 millimeters, no scale. This is 400 millimeters long. We're going to need that later. And then this one is 600 millimeters long. And it's an additional 600 millimeters this way. All right. So we have to convert that O2 to radians, right? So 0.02 degrees is equal to 0.3491. 0.3491. That's times 10 to the minus third, actually, radians. And you can do that either by ratio or calculation or use your calculator or whatever. But 0.02 degrees is not many radians. Okay, so now let's look at, we want this deflection here and this deflection here. And we're going to call this delta B, and we're going to call this delta C, because that's C and that's B. All right? Okay, so now we know that we have the angle, so we can say that delta B is just equal to theta times LAB. This is A. So this distance times that angle is just going to give us that distance, right? Now you could say, oh, but Mr. Wilt, we're supposed to use the sine because that's the opposite over the hypotenuse, right? Well, yeah, except that remember we said for small angles, you just use the angle. So that's equal to 0.3491 times 10 to the minus third times LAB, which is 600, and that's going to be equal to 0.2094. Okay? And then for delta C, that's going to be equal to, again, theta times LAC, and that's going to be equal to 0.3491 times 10 to the minus third times 1200 millimeters. And of course, that we have to use this whole length, right? That's where the 1200 comes from. And that's going to be equal to 4189 millimeters. All right, which makes sense that it's double this one because it's double the length. All right, so now I'm going to calculate strain. All right, so strain at B is just delta B over LB, and that's equal to 0.2094 over, we're going to get a really tiny number here, right? Remember, this is 400 millimeters. So this is all millimeters over millimeters. And that comes out to 0.524 or 524 microstrains. Right? So we carried a few extra digits up in here, and when we finished up, we kept the 3. And then the strain at C is, of course, delta C over length of C, and that's going to be equal to 0.4189 over 600, and that's going to be equal to 698 microstrains. Okay. Oh, did I slip up? Nope, I got it all on there. All right. So again, a couple of easy problems. Just use some some geometry and trigonometry, and remember, of course, our small angle rule here, right? I talked about in class. Okay, so what else? Let's do one more, and we'll do F2-3. And in this case, we have a parallelogram. We'll do a shear strain. We start off with a square, of course, and we shear that into a shape. This is point A down here. So this is A, B, C, and D. Now this is an interesting one in that we're going to shear it about A, this angle, but then there's also another change here and another change here. So it's kind of got quite a bit of change to it. And we're given that this height is 400 millimeters. This deflection is 2 millimeters. This length is 300 millimeters. And this deflection is 4 millimeters. Okay? So what do we do with that? We know that we're looking for the average shear strain at A with respect to X and Y. This is X and this is Y. So we're looking for the average shear strain here. Okay, so we have these two different angles, don't we? We've got this angle here, and we have this angle here. So those represent, in effect, two different shears, and we need the average. Okay, so let's do some calculations here. We're going to, let me zoom in a little bit for you. Maybe. Oh, there we go. Okay. Make sure you can still see that. There we go. So we're going to call this one alpha, and we'll call this one beta. So at alpha, we're going to say that that is equal to 2 over 400. And that is equal to 0.005 radians. Okay? And beta is going to be equal to 4 over 300. And that's equal to 0.01333 radians. Now, to find gamma at A, right, relative to xy, then we're going to say that this is at A, you know what I mean? We have to say that it's going to be alpha minus beta. And so that's just equal to 0.005 minus 0.01333, and that's equal to negative 0.00833 radians. And remember, shear strain is always in radians. That's it. Okay, I encourage you to do the last two on your own, fundamental F2-4 and F2-5, and then work some more strain problems, and that's all there is. Okay, thank you very much.